Thanks for coming to Tanner's Master's Defense presentation. Tanner, a little bit of the background, the Taylor Valley blood flowing through his veins here. Tanner did an associate degree at Community College in Abingdon, where I think we can blame Kevin for the most part for getting us here to this point and everything. And then he transferred to Virginia Tech, where he got a bachelor's in wildlife conservation here. And then wisely or astutely went up to Fred to work on a master's in forestry. Originally started solely under the direction of Dr. Carter, but was it you that caused Dave to move to Michigan? Or right. So somehow I inherited aspects of Tanner, but it's been a pleasure. I can say that. So, and Tanner, as somebody from the hills as well too, I know this, that when you're always going to be up against the 8 ball when you encounter a Yankee American or somebody from the city, and you have to work twice as hard to be respected. But I want to debunk some of those stereotypes of the time I've spent with Tanner about growing up in Appalachia. Those things I think that aren't true. So despite what people think, people from the mountains are curious about the world, how it works and everything. I think this is the one where you decided that power, not square, power around and everything. Okay. The one thing you can say about mountain folks is they're resourceful and everything. I guess you didn't have no pockets on that. They're open-minded and accepting of other ways of life and everything. But every now and then you realize, yeah, maybe the stereotypes are true. So the one thing that I say about Tanner is that I think you're going to see he did a quality master's and was a hard worker, and the goalposts were always changing and shifting, and I think we frustrate him at times and everything, but it's going to get him where he wants to go. He is accepted into the PhD program in range management at Oklahoma State, and he's going to go work with a guy named Sam Fullendorf, whom I've known for a long time, but is arguably the most preeminent range scientist, if not in the United States, in the entire world. And so I think that's to Tanner's credit that he's going to go work with somebody that's National Academy level. But going back to being a mountain boy, the one place I think that you picked where you're gonna fit right in, or maybe you're gonna feel superior, will be Oklahoma. So I think you're gonna thrive when you get there. Okay, I'll let you take over now.
Thank you for that wonderful introduction. And thank you guys for being here. Again, I'm Tanner Humbert, and we're going to begin with my first chapter, which is talking about forest stand structure and Virginia northern flying squirrel presence. Just some background on the West Virginia region. Between the turn of the century, around 1890 to 1930, an event called the Big Cut occurred across the Appalachian region, but really hammered the high Alleghenies of West Virginia. This was to make way for industrial America and eventually the world wars, where we saw nearly 30 billion board feet removed from the Allegheny Mountains. If you can't identify what board feet are, just imagine they clear cut everything they could get to, and what they couldn't get to, they burned it. After this era of really uncontrolled logging, uncontrolled wildfires broke out through the region, turning what was once pristine forests and spruce stands to moonscapes. This is Dolly Sods not long after the fire. This uncontrolled fires led to a limitation on seed sources for regeneration of other plants and specifically trees, as well as removed suitable soil conditions for many of the native plant species. One of those plant species being red spruce, which some accounts say that it existed in up to 600,000 hectares across the national forest. Hectares are 2 football fields beside each other. So that helps you understand how big. It was a big area. But today they only inhabit about 12,000 hectares. So a huge shrinkage of this once very plentiful cover type. Much of the land that was lost, that was originally red spruce, has regenerated back as a northern hardwood cover type, which is northern red oak, beech, birch, sugar maple, and some red maples, a lot of red maples, which is not particularly good for the focal point of this first chapter. The Virginia northern flying squirrel, that little bitey creature there, was listed as endangered in 1985 due to habitat loss and habitat degradation. But due to some efforts of cleaning up the air and getting spruce back on the ground, it was delisted nationally from the Endangered Species Act in 2013. But today in Virginia still exists as an endangered animal, and in West Virginia exists as an animal of conservation concern. This species, as you could guess, is a mature red spruce obligate, which means it's kind of indicative of decent red spruce sites. It is a Pleistocene relic along with red spruce, which just means it's left over from the previous ice age. So they really like that cold, high elevation climates. This animal is mycophagous, which means it eats on mushrooms and funguses, specifically a symbiotic fungus that attaches itself to red spruce roots, which is one of the reasons it really likes red spruce. It's a cavity nester, which means it likes to shove its head into a hole in a tree and likes to live there as long as it can. And the young males who haven't made a family yet dray nest. All dray nesting is a bunch of leaves piled between some conjoining sticks. Today, this animal serves as a barometer for how well we're doing in spruce restoration, because their population is directly correlated with a healthy core red spruce stand. In my study, I'm modeling habitat suitability. One of the reasons why we model habitat suitability in this region is because this animal's presence impacts the development of specifically private land, especially where there are species concern along West Virginia. It can really put a damper on recreational development and energy production, which, if you know anything about West Virginia, they're all about coal and they're all about hiking. That's kind of one of the two biggest things there. Another reason why we're modeling rather than doing traditional point counts or trapping is because in the past, standard nest box and live trapping surveys have proven to be very difficult due to the terrain and some of the unpredictable weather in the region, as well as acoustic monitoring has shown to have promising results as far as accuracy, but it's very hard to process once you get back home in the lab. I see people shaking their heads. So restoration actions need to prioritize promoting habitat connectivity and the quality of the core habitat while we can't really get our hands on the animal. So the next best thing is to build a proxy for habitat using habitat suitability models. Before I get into my model, I need to go over the 4 orders of habitat selection just briefly. First order habitat selection is our broadest category, which represents a region or the geographical range, the entire extent in which an animal can be found. If you're going to think about any of us in this room, your geographical region might just be the state or the East Coast, where you exist throughout most of your lifetime. Second order habitat selection I see as more of the town. This is the selection of home range for the animal, where it's going to spend its day-to-day activities or week-to-week activities. You know, go find food, go find mates, go find a hole to stick your head in. And then third order habitat selection, I consider the house. This is the core of your habitat range. This is where you're going to bring your mate back to rear your young. We're going to store food for the winter, and we're going to hide out if you can. Fourth order habitat is a lot finer. I like to think of this one as how you utilize the rooms within your house, as this specifically correlates with how animals use different components within their habitat. So some of the history of modeling for this flying squirrel, I stand on the shoulder of, I don't know if I would consider them all giant, but a long line of people who have worked their tail off to figure out what's going on with this little squirrel. Starting in 2001, Odom et al. Found that landform index specifically correlated with the absence of flying squirrel. So we could then take the inverse and say that a certain land shape is correlated to the presence of the flying squirrel. In 2004, Ford et al. Developed a third order habitat model, which showed increased occupancy with increased spruce composition, the threshold being anything greater than 30%. In 2006, a student named Menzel et al. Came out with a first order habitat that spatially determined zones relative to elevation and spruce proximity. So now we have spruce cover, landform index, and elevation floating around in the mix. In 2014, Ford et al. Made a second and third order model that showed squirrels selected specifically for mature / old growth forest conditions under red spruce. All mature old growth means is that you're late succession forest development with a large variability of both structure horizontally and vertically. In 2017, Diggins and Ford developed a microhabitat study, or fourth order, that showed a relationship between organic soil depth and understory spruce conditions to squirrel presence. And finally, in 2022, Ford et al., and there's a few people who work with the paper here, so I'm going to try to be accurate. They created a spatially explicit resource function using about 20 years of traditional animal trapping data and telemetry data with conjunction of random points they threw on a map that created a pseudo absence determiner. So now we have squirrel is there, or we don't know. So we have a 1 and 0. And they realized through that model that elevation, landform index, and red spruce cover class was highly predictive for the home range of flying squirrels within the West Virginia Allegheny region. Western Virginia and Western Maryland was also lumped in there as well. However, this model did not provide any insights into forest stand structure that could then inform on-ground forestry management with the purpose of developing either red spruce stands or flying squirrel habitat. So under the 2022 model, both of these sites end up in a high probability area. On the left, we have, I think anyone in here could argue that that's 100% red spruce cover right there at that site. Chris was there. He's seen this site. That's my technician, Henry. That's dog hair thick. If you don't know what that means, it's hair thick. There's a lot of trees. There's no understory and there's no midstory. It is completely a pole stand of red spruce. And on the right, we have a great diversity in structure, both horizontally and vertically, but the predominant species or cover type across this stand was hardwood, which we've already discussed that the flying squirrels tend to avoid. But you can see we have a decent mid-story of red spruce. That'll mean something later. So now I'm going to get into how I made my model and what my model means for flying squirrel restoration. My objective was to develop a model that could provide managers with tangible metrics and goals to manage to using traditional forest metrics. These forest metrics being stand height, the average stand height of trees, basal area, which is just the area of a circle at the cross section of a tree, summed up across the stand, and QMD, which is just the relative or average diameter across the stand. So how did I build this model? Well, I gutted the 2022 model and stole all of their 20 years of work of gathering presence absence data because I didn't want to go to the field for that. And I threw that into my model as the response variable. Then I went and stole someone else's work from 2021. TreeMap 2016 is a spatial raster product that spatially distributes estimations of forest stand structure across the United States. This provided me with that basal area metric I wanted, stand height metric that I wanted, and stand density, which is, in this case, was trees per hectare. All I needed left was some sort of metric for diameter. I then computed QMD in centimeters by using the square root of basal area over stand density and times, that's the Forester's constant for metric. If anyone here wanted to add another number to your list. I then utilized the Bayer's red spruce vector, which is what they used in 2022 to identify how much red spruce was available at any given area. And I slammed it all together, and now we have my model. I'm going to get into the model. There's a lot of acronyms, little 3-letter words or 3-letter symbols for words. I want to make sure everyone's on the same page. QMD stands for quadratic mean diameter. Again, that's just the diameter of a tree at breast height averaged across the stand. That's simplification, but that's what it is. Trees per hectare is just stem density across that stand. Spruce refers to the spruce cover class. O being 0% red spruce in the canopy cover, L being 0.1 to 10% spruce in canopy cover, M being 10 to 50% red spruce cover, and then H being anything greater than 50% red spruce makeup in that stand. BA stands for basal area, which is our stand-in for volume. And TH stands for the average stand height of dominant trees. And then this little thing down here just means that whatever the term is being used in that model is a quadratic term, which just means it has a it's not specifically linearly related to the response variable. That's all. They're still related. It's just a weird thing for modeling. So I developed a handful of models, and these were the ones I picked to be biologically significant. And then I compared them to each other using AIC. I'm blanking on the name of AIC, but all it does is compare model accuracy and parsimony. So can you predict or can you reach the true values whilst using the fewest amount of variables? I also used R squared, which is kind of the spread of this of their accuracy. And then I used AUC, which is the area of the curve, which is just how accurate the model can predict the points compared to the true points. And then I used the difference in AIC to arrange them. Our winning model was the flying squirrel could be predicted by spruce class, plus the quadratic of QMD, plus the quadratic of basal area, and plus the quadratic of tree height. But I do want to point out that the quadratic global, which included all of my variables at the quadratic form, was the second most significant model and had the exact same AUC, which means that all of these structure variables do play some role in predicting flying squirrel habitat selection, or if it can play some role. But diameter, volume, and tree height seem to be the most powerful. Besides spruce, we already know spruce is rowing the boat. This is a parameter estimate table. Don't get lost in the numbers here. All you need to understand is that not all spruce conditions are created the same. Spruce is driving the boat on all of these models. It is the most predictive covariate, but spruce is similarly, predictive when as the combined structure variables. They all have very low p-values, and they all have biologically understandable estimates with flying squirrel presence. So now what does quality flying squirrel habitat look like? I'm glad I asked myself that. From left to right, you can see on the y-axis is Virginia northern flying squirrel presence being 0% probability of presence, 100% probability of presence. And on the x-axis are stand height, quadratic mean diameter, and basal area, respectively, going across the list. Our first graph here shows that under the, and there's lines that are dictated by the spruce canopy class in which the conditions were under. As you can see, in all of our spruce canopy classes, squirrel presence peaks around 10 to 25 meters and then seems to taper off at the end. Our diameter, under diameter, squirrel presence also seems to peak between 10 and 30 centimeters and tapers off on the higher end. And then under basal area, squirrel presence seems to really get going after you get past 30 meters squared per hectare, which I have a conversion to standard later for you American folks. One thing to note is I personally believe by looking at my data that this little sweep down tail on both stand height and quadratic mean diameter are an effect of some outlying leverage points, as well as some of the assumptions you have to take on when you do pseudo-random points to predict habitat suitability. Meaning that we probably had a random point in a really tall poplar stand somewhere but we never had red spruce reach that height. Now, this is a fun graph. This is a graph that shows stand height as binned by basal areas across 15, 30, 45, and 60 meters squared per hectare, respectively. And what I want everyone to notice is that stand height stays relatively the same. The squirrel selection for stand height stays relatively the same across all graphs, but spruce compositions that are lower in composition than what previously thought for the flying squirrel do increase in probability for flying squirrel presence the more you increase basal area. This suggests that if you could have perfect stand structure, you might still be able to develop habitat for the flying squirrel. This adds to our understanding as earlier, as spruce is driving the boat, but not all spruce conditions are created the same. So what is optimal habitat on paper? It's roughly 10 to 30 centimeters in diameter, or 4 to 8 inches. It is 500 to 2,500 trees per hectare, or 200 to 1,000 trees per acre. It is 10 to 25 meters in stand height, or roughly 30 to 80 feet in stand height. And it is greater than 30 meters squared per hectare, or roughly 130 feet squared per acre. And of course, anything greater than 30% red spruce, you're in the money for flying squirrel habitat. So with this model, I wanted to output a couple of maps that could help managers really locate areas that need work and areas that don't need work. To begin, I developed a model that could tell managers where the optimal habitat is and areas where suboptimal habitat is, whilst also telling managers what is missing from that specific habitat. So I developed a categorical map in which the color changes with the additive dimensions for flying squirrel habitat. So a dark gray means that the stand's only meeting stand height, or only meeting the requirement for diameter, but it's not meeting anything else. It's probably a beach stand somewhere that's just roughly the height the squirrel wants it to be. When we get to light gray, we have all 3 structure metrics met, but we do not have the red spruce requirement, which means we have a perfect height, diameter, and basal area stand, but there's just little to no red spruce in that stand. Once the cell shifts to red, we now have the red spruce requirement. So a light red means that we are in a red spruce stand, but really the red spruce stand is only just tall enough for flying squirrel, doesn't have any of the other metrics for it. And then when we get to dark red, we now have the red spruce requirement and all of the required dimensions met for quality flying squirrel habitat based on my model. And this is what that map came out to be. I want to point out that the majority of the landscape is a light gray toward white, which means the majority of the landscape does have a decent combination of structure variables. Actually, it has about 45.6% of the landscape meets our requirement for structure, but does not have a red spruce component, which means that red spruce is one of our limited factors. This is something we already knew from previous works. Another thing I'd like to point out is that 36.2% of the landscape only meets a tree height and diameter requirements, which means as far as structure goes, volume or basal area is our limiting factor. The amount of area that contains all of our optimums only accounts for about 1,200 hectares, or 9.5% of the total study area. So we really need to get out there and get volume and red spruce on the ground. So then I developed another map that could show the spatial probability of flying squirrels. This is fairly a standard practice for modeling when you're modeling habitat. All this shows, I wanted the symbology to match the other ones so both maps can be used in tandem. So I use the same symbology. From 0 to 50% is gray, gradient toward light. And from 51% to 100% is red, gradiating from light pink to dark red. So if you're at dark red, you're near 100% probability that a flying squirrel will be there. If you're at white, you're near 50% that a squirrel will be there. Anything less than white or trending toward black means that no way, Jose, there's no squirrel there, or maybe no squirrel there. So now let's compare these maps. On the left is my probability map, and on the right is that categorical map I identified earlier. What I want everyone to notice is that areas of optimal structure match areas of high probability. This is my litmus test to tell me that the idea for the categorical map is hitting correct information compared to my probability map. Another interesting thing to show off that kind of supports a point made earlier is that areas that are a light gray within this circle are areas of a light to medium red in that circle, which just points out that there is an above 50% probability that flying squirrel will be at a stand that doesn't quite meet the spruce requirement, but does meet its structural requirements. I just found it cool. Now let's compare my model to the 2022 model. 2022 model was a home range model, so it's not super fair to compare the resolution, but I think this highlights the importance of a third order model. With the 2022 model, I could tell you that Tanner spends most of his time in Blacksburg or Abingdon, his day-to-day life. On my model, I could tell you that Tanner lives on Thomas Lane and Shell Road, respectively, at those places. That's kind of the importance of both models. What does this mean for management? Well, this now gives us a way to manage not only hardwood dominated stands, but spruce stands. I would come in here to this 100% spruce stand and I'd kill a bunch of shit. I would knock down, I'd do a row thinning, and I would free up some resources for the selected red spruce to live and allow them to get wider and taller and eventually reach that volume metric that we want. And what I would do over here is what we're already doing on spruce restoration. I would select the canopy competitors of these 3 or however many red spruce are within this stand, remove the hardwoods, and let the red spruce take the canopy. We would maintain that variable late succession structure that we want, whilst also getting red spruce canopy. And over here, we would eventually develop. We would allow initiation of mid-story and understory to happen. What does this mean for you forester managers out here? Well, if we take a stocking chart, you want to manage any forest within this range or below this range so it could then grow into that range. If you're not a forester, just ignore this. This is a stocking chart. You want to be within the zone of optimal density management. It is primarily, I would theorize that anywhere along that line, you're going to eventually get flying squirrel habitat. So my chapter 1 conclusion is a structure model adds, well, structure variables to our understanding of flying squirrel habitat. This can be more useful in habitat assessment and restoration along the range. This can provide better information to land managers on what they need to do and where they need to do it. And this can also provide us an idea of better selection for spruce conditions to manage for. This also provides a more accurate estimate in the connectivity of flying squirrel habitat quality. So we now know that between patches, we don't have any connectivity. We need to get some corridors going and connect the patches. Get some water. That's enough of that. About half you in this room didn't come to hear about a squirrel. We're going to talk about red spruce. Admittedly, to me, I like the squirrel, but I didn't get to hold one. I did get to hold a red spruce. So my chapter 2 is about the crop tree release study that happened about 20 years ago that ultimately released these red spruce into a mid-story and not really a canopy position. So in 2005, a doctor named James Wrench from the University of West Virginia set out to do a simulation on red spruce release. Him and his colleagues went out and selected 188 red spruce under 6 sites and projected a 6.1 meter cylinder around that tree and virtually selected the canopy competitors and removed them. And under the simulation, he wanted to test how the new light conditions would grow the red spruce. Well, in 2007, he got to do it in real life. He got some money and he got some people and he went out there and did it. He released them under 4 conditions. One was a 0% release, means he did not touch anything. He just went there, nailed a nail and a tag into a tree and walked away. The low basal area removal treatment was a 33% The median basal area removal was 67% basal area removal. And the high treatment was a 100% basal area canopy competitor removal. It's important to note that he did not explicitly remove lateral competition. So any trees that were relative height or shorter to the red spruce were not touched. And here's a pretty little map for all the 6 sites across West Virginia. So on paper, here's what spruce release looks like. You draw your 6.1 meter cylinder, you find out that you have a canopy tree directly impeding the growth of your red spruce. You knock it down, you walk away and let it grow, and eventually it would capture the canopy. So in 2024, we wanted to see if this happened. We went out, me and Abby and Chris and Henry went out in the hot months of June and July. Well, it was hot for you guys. It was pretty nice for us in West Virginia. And we were able to find 182 treated trees. About 42 of them, or not about, exactly 42 of them were controls and 140 of them were treated. We were able to find all 6 sites despite no accurate GPS points. And at those sites, or at every individual tree, we got the total height of the tree and the diameter of the tree, as well as new fancy sub-meter GPS points at each tree. So the next tanner doesn't have to waste 2 or 3 days trying to find these trees. And here's what we found. We found that from 2005, the trees have been steadily growing. Now, I know this looks like an exponential curve. I want to remind everyone that Wrench's last measurement was in 2013 and my measurement was in 2024. There's 11 years of missing data between the most recent measurement and the one before, which means that these lines are probably more linear than they are curved, but there's probably a little bit of curvature in there. Another thing I want to point out is that these trees were released in 2007, and you don't see any differentiation between the treatments until we get into 2010, 2013, and then of course, 2024, you can see that our 100% released trees are growing quite a bit more than our controls. And the medium and low treatments are fighting to see who wins a second place battle. I also wanted to get an idea of growth rate per measurement year. So what I did was just subtracted the value of the previous year from the value of the present year and divided the amount of years, between the current year and the previous measurement year. So I subtracted the value of 2005, that's why it's not here, from 2007, and then I divided it by 2. Everyone on the same page? Or, yeah, 2. And what I found is that the growth rate for both height and diameter immediately slowed down after the trees were released. This is something that I've heard called treatment shock for a lot of trees, especially in like open canopy releases like this on shade tolerant species like red spruce. But that growth rate really quickly accelerates after it gets over its treatment shock, and diameter stays relatively the same 11 years later, but our height growth rate has shot down to below what the growth rate was at 2007. What does this mean? This means that not removing that lateral competition or not opening up the gap wide enough or a mixture of both allowed for things like red maple and the canopy to close back over top of our competitive tree and slow it down on its growth rate at some time right at 2013 or beyond. So what does this mean for management? Well, across the ground, people in TNC West Virginia are relatively doing, or pretty standardly doing, group releases where they find large patches of red spruce in the mid-story and killing anything that's not a conifer and moving on and letting red spruce take the canopy and figure itself out. Alternatively, we could do a re-release of these same plots after 6 years. You could release the tree, come back out, and re-release it 6 to whenever that growth rate starts to slow down. But you would have to make sure you remove the lateral competition. Otherwise, that red maple is just going to take the spot again. We could also double or even triple the gap size around these trees and keep from peripheral canopy competition from closing over top of the tree, or we do a good old shelter wood. You go out and you kill all of the lateral competition in the understory, let the trees get up to a just under canopy position, and then go out and remove the shelter, remove these canopy trees. You could also do this with a deferment cut or a retention harvest, where you leave some of the sheltering trees for wildlife benefit or whatever else. But perhaps most controversially, we could do nothing. And red spruce, seemingly, at least in the climate context of 2010, is winning against northern hardwoods. They're just playing the long game, and we don't live a long time. So there's evidence for all of these. I personally think group release will probably get us to our goals the best. But if we did nothing, it seems that climate change remaining the same, red spruce would win. But we don't really know how climate change is going to change in the future, which is why we want to manage this now. So my conclusions: single tree release of understory red spruce really only releases it to the midstory. It does not get it all into the canopy. The tree just doesn't grow faster than the maples can grow over it. To achieve true canopy capture, we need to make gaps wider. We need to remove lateral competition, and we may even still need a secondary release of these individual trees. I also learned that red spruce is pretty cool, but I could see how someone working with it could get annoyed very quickly, because they really don't like to win, or at least they don't like to win on your terms. They'll just hang out. Don't take a breath yet. I did 2 more things, and I think they're pretty cool, so I'm gonna make you suffer. I did a LiDAR thing. While I was out there prancing around on someone else's study, I joined Abby to prance around on her study, and I measured a lot of her target trees' total height. I then brought this home and put it on a map, and now I have a metric for ground validated tree heights. I used this new metric to test the accuracy of both TreeMap 2016 and LiDAR derived Z maximum heights. All Z maximum heights are the tallest heights of the canopy classification for LiDAR points. And anyone who doesn't know what LiDAR is, the easiest explanation is a 3D picture of the forest. So these Z maximum heights should be fairly accurate in our thinking. I also use these Z maximum heights to develop an index for surface canopy roughness, or CRI. And then I used both this CRI and these LiDAR derived heights to again test and see if they're correlated to flying squirrel presence. The height validation worked fairly well. As you can see on the left, LiDAR heights are fairly correlated with ground heights. Someone could make someone a little bit smarter than me could probably make a conversion factor, and we could apply those to LiDAR heights and get within an estimate of error to what it would be like on the ground. TreeMap 2016 was much less correlated to ground heights. TreeMap 2016 is a course product that was developed for rough estimations of structure and wasn't really designed for being utilized at a fine scale like we were trying to use it. But back in 2023, it's what I had to make a model with. So don't throw tomatoes at me just yet. What canopy roughness is just a metric that identifies the variation texture across a canopy surface. A low canopy roughness is this light texture that if you were to run over with a Jeep with really stiff shocks, you'd be able to keep the baby in the back asleep. If you run over this texture with the baby in the back, the baby is going to have CTE syndrome for the rest of its life and probably bust its teeth if it's got it. I then normalized this metric of height by dividing the standard deviation of the target cell and surrounding cells' Z maximum heights by the average height at the target cell and surrounding cells. This allowed me to compare tree stands that were of vastly different tree heights. I could compare them on the same metric fairly. And if you don't know what that is, it's called the coefficient of variation. It's this little thing right here. And here's what I found. I found that canopy roughness is positively correlated with flying squirrel presence under all canopy or under all spruce canopy classes. Even our lower one starts to increase a little bit the rougher you get. This is probably because canopy roughness is indicative of mature or late succession stands, as tree mortality happens the older you get. I also found that the LiDAR heights are positively correlated with flying squirrel heights. If you remember my bell curve from chapter 1 on flying squirrels heights to the tree map heights, or flying squirrel preference for the tree map heights, now we have straight lines. This kind of further supports that I had a few leverage points at tree map, but I do want to point out that we get above 50% probability at the 25-meter mark. So this means that at least the direction the relationship is going for tree map is correct. And if we just use the 20 to 25 as a minimum for tree heights, we can still accurately manage for flying squirrel. Because in my brain, biologically, there's no reason why a tall tree wouldn't work for a canopy dweller. So to conclude, Tree Map 2016, while of course still provided enough information to elicit somewhat accurate relationships between flying squirrel presence and tree heights, LiDAR-derived heights are closely related to ground-verified heights, and canopy roughness index has a positive relationship under all spruce classes with flying squirrel presence. Now, everyone can take a breath. I'm going to thank people, and then I'll get out of your hair. I'd like to thank everyone who made this study possible, specifically the funding from the U.S. Geological Survey and the funding from the Northeast Climate Adaptation Science Center. I'd like to thank our friends at the U.S. Forest Service, specifically Shane Jones, Jason Teets, Chris Henning, and many, many others who unlocked gates and sent maps and emails and warned us about roads being missing and all sorts of fun things. Long conversations with Jason Teets. I'd like to thank our friends at the U.S. Fish and Wildlife Service, the Canaan Valley Wildlife Refuge, Matt Borman. He allowed us to work on 2 of the wrench sites, gave us access to that area, and also allowed us to sanitize our boots so we weren't messing up other people's research. Very nice people over there. Go visit the wildlife refuge if you can. I'd like to thank everyone from the Forest Resources and Environmental Conservation Department here at Virginia Tech. Without you guys, I wouldn't have had a master's degree. So I think it goes without saying, thank you. And I'd like to thank the Nature Conservancy of West Virginia, specifically Will Evans, for being super responsive on emails and super forthcoming about their methods of spruce release and maps and history of spruce release within the organization. I'd like to thank the people who came out to the field with me. Abby just ran off, but Chris Harris, who is here, Henry Cottigan, who couldn't make it today, and my lab partner, Abby McKellips, who this project would have never happened without because she is super fast on emailing, really quick to call and get in contact. She's organized and she's on it. And without her, I wouldn't have made it through the summer. I'd also like to thank Ben Protzman and Kristen Beasley, who I don't have pictured, for coming out on a last minute July excursion to finish up our sites. I'd like to thank some of my friends who worked with me in the previous years or visited me in the field, notably my current roommate, Clay Coleman, my arch nemesis, Ava Moltner, and my long-term mentor, Julia DeFeo. And of course, my friends, Jolie Basson and Ryan Atkins, for coming to visit me during my field work. They made a long summer a lot more palatable. I'd like to thank my family for showing up or watching. My aunt and uncle, Kimmy and Daniel Necessary, my nephew and cousin, Elijah and Jacob, my big sister, who's holding a very grumpy Tanner, Keisha Necessary, my 2 moms, my memo and my mother, Robin Necessary and Trisha Grindstaff, for feeding me and making sure I'm okay. And of course, the man, my papaw, Tommy Necessary, for always giving me advice, sometimes advice I don't understand, but he promises it'll make sense someday. But now I need to thank the group of friends who got me through undergrad, got me through a degree at community college, and have now got me through a master's degree. Without Austin Holloway, Ryan Atkins, Kaylin, and Nathan Ferguson, I wouldn't have got up for tests. I wouldn't have woke up to go to class. I wouldn't have gone to work hungover. I wouldn't have rolled out of bed to make breakfast. And without that little dog and that little cat, I wouldn't have had anything to do on days that I had nothing to do. And without this man right here, I wouldn't have known that this job field was even available to me. So another special thank you to Kevin Hammond for just showing me how much fun you can have in the mud with salamanders and getting hit by trees. With that, I'll take any questions.
Well, you unwisely left 15 minutes for questions, so here's your chance.
Zoom's clear for now.
Okay.
So red spruce is now kind of restricted to higher elevations.
Mhm.
So you're feeling it's working its way lower. What do you think is the lower limits for red spruce elevation?
So in my model, I limited everything to 800 meters elevation because that's about as low as we found them. But we do have evidence to suggest they can be lower if they are in wetter conditions. The Sky Island issue is a separate issue from what Rollins was kind of getting at. I don't think they'll ever be able to work their way back down the mountain unless we have some sort of adverse climate change or a new ice age. They retreated to the Sky Island refugia after the last the glacial recession, and they kind of stayed there.
You don't think it's hardwood competition driving that?
I think to an extent, hardwood competition is keeping them up on the mountain. But I think in these low, drier, and warmer valleys, like the Greenbrier Valley, I don't think red spruce would stand a chance. And just the open sun all day long, or even on those more xeric southern aspects.
At what scale did you calculate quadratic mean diameter? Was that at like a stand level, or did you do it?
It was an average stand level scale because I used tree map to quantify it, and tree map is a rough average stand level scale. So it wasn't like individual tree diameter, it was just average diameter across the stand.
And for your average diameter or whatever was available for tree map, do you think there was enough variation like in that data for your quadratic mean diameter and the impact it has on your model to not be biased in any way? Like, did you see like plenty of larger diameter?
Oh, yeah. There's a lot of large diameters. There's a lot of information for some of the really big poplar stand, or not poplar stands, but poplars, some of the really big cherry stands out there in West Virginia. And tree map did pick up those. There were, the reason why it pocketed was because there were a ton of points that were considered negatives. I think they're false negatives, or they're not necessarily false negatives, but they're just not being fair to red spruce that were in bigger diameter classes.
And I'm probably ignorant to it, but so you're talking about the actual red spruce, like stand manipulation. Is there any concern with, so historically they were doing kind of these tighter releases, right? And now you're talking about potentially larger releases to perpetuate that further into time, right? Is there any concern with things like wind throw or induced mortality in that regard, right?
There would be if the trees were taller. Specifically under the wrench study, they were very short trees, like roughly 10 foot. So even you could even double that gap. And at least from my knowledge of it, the wind would still be shielded on all sides of that tree from the surrounding integral forest. Now a spruce on the edge, if it got released and it was also fairly tall, that big fan, rip it out of the ground.
And the high elevation.
Yeah, yeah, absolutely. But these are fairly sheltered even in release.
Yeah, so this one's for me, not from Zoom. So kind of building off that, you talked about expanding those gaps and even the road thinning in that dog hair thick stand at one point. In hardwood stands, I know the crop tree release research shows that the stuff we see in the understory isn't necessarily stuff we would want to see in the overstory and the advanced regeneration. I know red spruce is long lived, but in terms of that, what do you think the management implications are? It's like, yeah, we successfully got the red spruce for our generation, maybe the next generation, but for future management,
Yeah.
those undesirables, what do you think would happen in that understory by expanding those gaps?
So red spruce do live in mesic sites, and I think saying mesic cues an exclamation point on every forester in here when that involves a threat of red maple. Right, it's just red maple were the ones we saw beating the red spruce just observationally. I don't think you're ever going to get rid of that threat of red maple unless somehow we can make a site xeric enough for red maple not to be there, but able to maintain spruce. There's always going to be there. I think to me, it's more important to get that structural diversity than to necessarily sweat over what's going to come back until it comes back. So these treatments may need to be more hands-on than, say, an oak treatment of some sort. But I don't think we can get away from things like red maple or even beech.
Hey, thanks for the presentation. Really, a lot of really interesting work. I'm curious about you had shown a graph of growth rates after the canopy release.
Mhm.
And I noticed that the control trees they seem to have a similar pattern in terms of change in growth
Mhm.
rate to the treatment trees.
Mhm.
And I'm just curious why that is.
This is something you can ask Ford about. I sweated over for months. And the best explanation I have from surrounding research is that all these trees are reacting in a similar shape to how growth situations are changing along the time scale.
Right.
Because in theory, in Wrench's original theory, we should have seen a flat line on the controls and a boom in everything that was treated, and a huge separation. But it doesn't, like the line, you can see that there's curves on the fully released trees, follow the same curves on the control trees. You can even see that in this graph. I think this goes back to what Rollins was saying in 2010, that these trees are still growing and are still working their way to be competitive for the gap. But treatments like this, or specifically group release treatments, in my opinion, can work to accelerate red spruce beyond or to a faster time scale to maybe beat and make a resilient stand for climate change. But yeah, I was worried about it too. I'm like, well, does this mean they mean nothing? And I was assured that it doesn't mean they mean nothing.
I think this is good news. It shouldn't surprise us that a long-lived shade palmer can do that, just periodically wait for periodic releases over 400 years. And there's no way you're going to get around to a million acres to do anything hands-on. So I think, climate change aside, Rollins was right, that it's still trying to recapture at least most of that former distribution, going back to your question, at least over there. It's just, do you want to do it in 75 years or do you want to do it in 300 years?
I came to the conclusion that these trees can be 400 years old, and to them, waiting a quarter of their life to be on top for the rest of their life isn't that big of a deal. But for us, who wants to see the benefits that red spruce provide, like nitrogen sequestration and carbon sequestration, we need to release these trees on a larger scale and at a quicker scale. Any other questions? Did I answer that?
Yeah.
Okay.
Can any of those release sites be done on a commercial level, or is this all conservation?
I'm glad you asked. They have released not red spruce, not the study sites, but West or TNC have done commercial releases that can help with this, the group release specifically. They can find a large patch of red spruce that might be surrounded by northern red oak. And they have enticed loggers to come out, grab those, make their money, and also release the trees. So yes, absolutely, we can do things with commercial release. We can't do everything with commercial release unless you're Martin Guitars and trying to release, harvest a bunch of small red spruce.
Still clear on something, buddy.
Okay. Any other questions? The more y'all ask me, the more time I can get between them. So please ask me. I wasn't nervous about this. I'm nervous about him and him. Specifically him. Look at that grin. Well, I thank you guys for coming. Thank everyone on Zoom for watching.
Nice job, Tanner.
Dave, I'm gonna cut the Zoom meeting here and I'll recall you on Zoom when we get back to the glass room. Is that okay?
Sounds good.
Your classroom, I think.
Here's
Yeah.
Yeah.
okay.
should automatically say.
It'll automatically, so you don't- Okay, I could scarf my lunch down.
Yeah. You want to just